Hello, this is the second part of the SunAngle Lab that deals with the 10 short answer questions that are linked right here. You click on this link and it will open up 10 short answer questions, and you will basically type out these answers. In fact, when you click on the link, you should see this file right here open up, and you can actually answer your put your answers, and I like to see the question and answer together. And if you can just answer these questions and put your answers in red so it's easier for me to follow, that would be great. These 10 short answer questions all basically are evolving around you having your 4 graphs developed for the tropical, polar, mid-latitude, and subtropical regions. And if you have those graphs done, you should be able to answer these questions very quickly. So what I would like to do is I'm going to answer or give you some clues about what these questions are trying to address, and hopefully when you're answering these questions, you'll type out these answers in red and just save this file and attach it with your graphs, and you'll have your graphs and short answers, and your 20-point lab will be submitted in 2 parts, and you'll submit both the graphs and the short answers together as one file, or as one assignment. And so you'll have 2 attachments. Probably your Excel file for your graphs and your short answers will be attached to separate files to the SunAngle assignment submission. Question 1. Why do you think temperatures change very little throughout the seasons based upon SunAngle variations for the tropical locations? So for this question, you'll get out your tropical graph, and what you should be looking at in particular is you should have your tropical graph up, and what you're looking at is we're trying to ask is why would you expect throughout the 4 seasons based upon your SunAngle profile, why would you expect the temperatures not to change much over the 12 months? And you should be paying very close attention to, does the sun angle change a lot, or is it always relatively high? If the sun's angle is always above 60 degrees, for example, that would mean the sun's angle was always very high. But if you see this, and that would cause the temperatures to be very similar throughout the year because you're getting about the same amount of radiation. But if you see the sun angles going from the 80s and 90s and down in the 20s and 30s, that means your sun angles are changing quite a bit, and that would mean a lot or more or less energy at different times causing the temperatures to change. So get out that tropical graph, and if you did it correctly, it should be very clear to you why the seasons don't really see a massive change in temperature in the tropical locations. For question 2, why do you think tropical regions never experience winters like mid-latitude? So you'll have your 2 graphs, the mid-latitudes and the tropical region, and in particular, look at the low sun angle time of the year and compare what the lowest sun angle is of the mid-latitudes, like where we live, and compare it to the lowest sun angle in the tropics, and you'll really understand why does winter feel so differently, say in Chicago, as it would, say, in Rio de Janeiro, Brazil, near the equator. And it really would be the difference is when is the sun at its lowest angle. For question 3, this is a great question, is what's the lowest sun angle you calculated for the tropical locations? So when you look at the lowest sun angle for your 3 cities in the tropics, what was the lowest the sun angle ever got, and compare it to what was the highest sun angle you ever got in the polar regions. And what you should end up finding out is even when the sun is at its lowest, the sun angle is always higher in the tropics and the polar. So on this question here, you would give me a number for the highest or the lowest sun angle for the tropics, and what's the highest sun angle in the polar region, and you'll really understand no matter what time of the year, you'll see that the sun is almost always, well, it is more direct in the tropical locations for any time of the year. Questions 4 and question 6 are very different, and I'm going to save those till the end because they have to deal with the surface area heated, and I would argue questions 4 and question 6 are related to using the surface area heated formula, and I'm going to do those questions last. Question 5, Why do temperatures in Brisbane, Australia seem to be warmer when compared to temperatures to New Orleans, Louisiana? Now remember, Brisbane, Australia and New Orleans, Louisiana are both in the subtropics, but why would you hypothesize that Brisbane's temperatures are going to be at their warmest when New Orleans temperatures are going to be at their coldest? Pay careful attention to which hemisphere these cities are in, and you should be able to answer that question. For question 7, we're skipping question 6. Question 7, why do temperatures in Galesburg, Illinois appear to be very similar to that of Mukden, Manchuria? Well, these two cities are very close. Well, they are in the same region. They're both in the mid-latitudes. And even though they're half a world apart, one is in Asia and one is in North America, pay close attention to the latitude, and it should be very clear to you that even though these two cities are thousands of miles apart, the seasons might behave very similar in these two cities. If you understand the latitude of these two cities, it should become very clear. Question 8. For all polar regions, all the cities in the polar regions, there are specific times of the year where the sun never rises above the horizon. True or false? So what basically I'm saying is, for every city you have in the polar region, every one of them has a distinct time of the year where the sun never rises. So that means that at least for one of your seasons you have a negative number. If you have any city that in the lowest sun angle of the year is still above 0, you would have to answer false, because that would indicate that you would have a city that at least would have some sunlight during the lowest sun angle of the year. And that would basically mean they're not getting 24 hours of darkness. Question 9, why are temperatures in Barrow, Alaska, why would they might not ever get above 60 degrees Fahrenheit, even though we know near above the Arctic Circle they get 24 hours of daylight? So the key here to understand this is have you really caught on to the power of the sun angle to control the power of the radiation? That really will come from understanding questions 4 and 6. So even though Barrow, Alaska is getting 24 hours of daylight, why might you hypothesize that the sun angle or the temperatures might not ever get above 60? You need to pay close attention in summertime. What is the sun angle in Barrow, Alaska to begin with? And that'll give you insight of why the temperatures might not ever get that hot. Question 10 can be somewhat tricky, and all you need to do is tell me during the summer solstice, during the winter solstice, and during the equinox, of all the cities, what city is getting the highest sun angle during each one of these seasons? So all you have to do is look through your 4 graphs and all your calculations, and what city is getting closest to a 90-degree angle during the summer solstice, during the winter solstice, and equinox. It should just be the name of one city. So for example, if you know during the equinox the sun is directly overhead the equator, you should be targeting a city that probably is the closest as possible in latitude near the equator. Now I want to go back to questions 4 and 6. In questions 4 and 6, they get back to understanding of a concept that is called the surface area heated. And that goes back to this animation right here. And it's in the lab itself. As the sun angle changes, the area on the ground changes as well. And as you watch this animation, notice as the sun angle gets lower, how much the surface area on the ground heats. So when you run the animation at 90 degrees, when the sun comes in at 90 degrees, the area and the circle on the ground is very tight. That means that the surface area heated is very small and the radiation is being packed into a very small area. As the sun angle gets lower and lower, you will notice that the surface area heated by that angle gets greater and greater. And as you move away from the equator, like towards Canada, as you watch it again, as the sun angle, as you get away from the subsolar point and the sun angle gets lower and lower, you see that the surface area heats heated gets greater and greater. We actually have a formula to calculate how much stronger or how much weaker the sun angle is. So for example, if I was to do a 90-degree sun angle, at 90 degrees you would calculate, and you could use the Windows calculator, and you could bring up a calculator. All you would do is type in 90, and you would take the sine of it under the trigonometry function, and you would get the number 1. And if you took 1 and divided by 1, you would get the number 1. And so what that tells you is when the sun is coming in at 90 degrees, the surface area heated is exactly equal to what it is at the top of the atmosphere. And that means that is direct sunlight and very powerful. Now, if I drop this down to a 30-degree sun angle, I want to do the same calculation. And I do this example for you in your notes. There's a 30-degree sun angle, and notice how much greater that angle is. And if I came here this time and went 30 degrees, and I used a trigonometry function, and I took the sine function, I took 0.5. If I took 1 and divided by 0.5 now, I would get the number 2. And what that means now is at a 30-degree sun angle, which is the sun angle we get during winter, the sun angle is now heating an area twice the area that it was when it was actually coming in at 90 degrees. So a 30-degree angle is heating a surface area twice the surface area as it is when it's coming in at 90 degrees, and thus it's about 50% as strong as it is when it's 90-degree sun angle. That's why during the wintertime, when we get a 30-degree sun angle, we're getting a much weaker solar radiation than areas closer to the equator that are getting closer to a 90-degree sun angle. And that's why polar regions obviously have much weaker sun angles. I just wanted to show you this example here, so when you're asked on questions 4 and 6, you kind of get a sense of how to interpret and do the math for doing the surface area heated. So I will stop the video there, and I hope that helps you answer questions 4 and 6, which I think are the trickiest. And obviously, the bigger the surface area heated number, the weaker the solar radiation, the smaller the number, and 1 would be the smallest. So when you do this animation here, the strongest solar radiation you can get is a solar radiation of 90 degrees, gives you a surface area heated of 1, and that's the strongest solar radiation you can get. Again, I hope this helps you answer the short answer questions, and let me know if you have any questions.